so I didn't mind recycling it for you guys. And I figured you guys probably wouldn't mind watching it at your leisure. Okay, so let us begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to just bless our work today. Help us to glorify you what we do. In your name I pray, Lord Jesus. Amen. So I'm going to talk about case-wise defined functions to start with. And so what we'll do is we'll just work a few examples of these. For each example, I'm going to give a formula. I'm going to show you how to evaluate some points for the formula. And then we're going to graph it, and we'll talk about the properties of the graph, okay? So that's going to be what we're going to do here. These are, I think section 2.7 has these problems in it if you're keeping score. Maybe it was 2.6 actually. Oh yeah, 2.6, my bad. Anyway, so example 1. Suppose we have f of x equals 2, 3, if x is less than or equal to 0, and x squared plus 1 if x is greater than 0. So this is a very silly function, but let's try it out for size here. So what happens when I plug in, for example, f of minus 1? Which case am I in, the first case or the second? X is less than 0, right? So I have to follow instruction up here, and what's the formula? 3. Okay, yay. And like what's f of minus 10? It's 3, right? F of any negative number or 0 is 3. It's a very boring formula, but there it is. F of 0, 3. Okay, how about f of 2? Yeah, 2 squared plus 1, also known as 5. I guess I could look at f of 1 also, right? 1 squared plus 1, 2. Okay, so in each one of these cases, let's talk about the point on the graph that we get from each one of these, right? So I get the point minus 1, 3 is on the graph. This tells me minus 10, comma 3 is on the graph. This tells me 0, comma 3 is on the graph. This tells me 2, comma 5 is on the graph. This tells me 1, comma 2 is on the graph. These right here point on y equals f of x, okay, the graph. So let's graph it. Let's see here. So it's pretty silly. For y equals 3, for x less than or equal to 0, pretty much I have this. Now is this, should I put a solid dot here? I think I should, because it's less than or equal to 0, so I indicate that the value of the function is right there by that solid dot like that. This point is technically 0, 3. So here's y equals to 3 for x less than or equal to 0. And what's the other case? X squared plus 1. What is x squared plus 1? That's a, if I just asked you to graph y equals x squared plus 1 on its lonesome, you should be able to do that, right? It's a parabola. The vertex is 0, 1. It opens, you know. This is y equals x squared plus 1, right? We know this already from our work with parabolas. But now we don't want all the parabola, right? Because we're just doing what? X squared plus 1 if x is positive, right? So I put a open circle down here, and then I've got like the point 1, 2, which would be something like here. And then I've got the point 2, 5, which would be here-ish. So it does like this. So here we're looking at y equals x squared plus 1 for x positive. So altogether, this is the graph of the case-wise defined function f of x. All right? There are two different cases, the purple graph, the red graph. Man, I somehow managed to not talk. I mean, I mentioned the vertical line test, I think, in the previous lecture, but I didn't really show it. I'm going to have to circle back to that. Not so much today, but maybe like next class. That does need to be discussed more. Sorry, my mind skipped a beat and didn't do it, but I usually do that first lecture I talk about functions. So guys, can you tell me what's the domain? So can you guys tell me in words, what is the domain of f of x equal to? So it should be the x values which are allowed for the formula or the graph, right? So in this formula, I have an instruction, right, a recipe, if you will, for x less than or equal to 0. And I've got this other recipe if x is positive. Every real number is either positive or non-negative. That's everything, right? So the domain here is all real numbers. See these arrows? They go on and on. So the domain is just this. What's the range? That one's more interesting. So the range would be the y values which the graph actually gets to. Which are those?
3.
Well, it definitely gets to 3. It covers 3 quite a bit. Yeah.
The other one. 1, 2,
2, 3, 4, 7. What do we got? So here's this point right here is 0, 1, right? At the bottom there. That's as low as it goes, right? So the range here would be 1 not included to infinity. See, because wherever you go above 1, there is always a y value, which is, every y value is hit, right? So that's the range here. And if I was to delete the purple case, it wouldn't change things, right? Wouldn't change things a bit. Example 2.
How come if you were to delete purple case, how come the domain wouldn't just change?
Oh, well, the domain would not be minus infinity to infinity anymore if I was to do that. That's true. That would change the domain. Here's another one. We could look at y equals to, well, I just want to, excuse me, we could talk about f of x equal to, this one will have 3 cases. All right, you guys ready? 2 plus x if x is less than minus 4, and then minus x if if minus 4 is less than or equal to x is less than or equal to 5, and then 3x if x is greater than 5. That's nice. All right, so let me just give you kind of 3, maybe 6 sample values, all right? So what would f of minus 5 be equal to? Yeah, 2 minus, so minus 3, right? Very good. What would, let's say, f of, oh, I don't know, minus 10 equal to? Right, we're still in case 1, right? So you're like, do something different, right? So there's minus 8, great. What would f of minus 4 be? Yeah, minus a minus 4, also known as 4, very good. And let's see here, what would f of, let's say, 5 be equal to? Right? Oh, yes, negative 5. Thank you. So we're still in case 2. Let's see here. So let me do some color coding to kind of explain what's going on here. So let me say this is case 1. So that would have been both of these guys, right? And both of these fit into case 2, right? And then let's see here. How about f of 6? What's that? F of 10, what's that? Yeah, 3 times 6. And then 3 times 10, 30, right? Because we're in case 3, which I will make green. All right, now we can graph this thing, right? So oh, you got me. Cool. All right, so
I have a question.
yeah.
How do we know when to change cases?
Well, you have to think about which case the number fits into. So it depends on the instructions. Like where does x fit? Is x less than -4? Is the input between -4 and 5? Is the input greater than 5? Like it depends on where the input fits into that story. That's how we have to decide. Now it might be helpful, like I think it's helpful maybe to draw a picture for these kind of functions. Like maybe that's helpful. So here's -4. Here's 5, right? And so if you look at it, we really have either y is equal to 2 plus x over here, right? We have y equals to minus x in this case. And we have y equals to 3x in the third case, right? So depending on where your x is, you use the appropriate formula, right? You can envision -5 is over here, right? -10 is over there. And then well, the 4 is included in that case. The 4 and the 5 are both included in this case, right? I don't have a way to make my picture good for that, but then 6 is like over here, right? And 10 is over there somewhere. I mean, so that's why I used the formulas that I did in the cases that I did, because that's what the recipe says, right? Now, excuse me. So the points on my graph, I've got -10, -8. So, let's see here. I guess I'll make that about here. I may regret that. I may regret that. But anyway, here it is, -10, -8. The other point was 5, -3. So here-ish. And that continues on until I get to -4, which let's say is here. So there's like an open circle here. Right, now this goes on and on, right? That case goes on and on, the purple case. Now case 2 goes from -4 to 5. Now, where does it start? It starts with -4, 4, right? So -4, 4 would be like here. That's included, right? It goes to 5, -5, which is kind of like here-ish. You know, if I had some graph whiteboard, I could do better, but I don't. So f5 -5 at this point, right? So this is the graph of, and how about case 2? Does it go through the origin? We're doing what? We're graphing y equals -x, right? That goes through the origin. Has a slope of -1. So it's, it's this thing. All right? there's that, and then what happens? Then we pick up the story at 3x at 5. Now, it's not in the case, right? But if there was equality here, we'd have a where. We'd start where? We'd start at 15, right? Now, we don't actually do that because it's an open circle here. But at 5, we jump up here to 15, which is like here-ish. So that point would be 5 comma 15. And then it's 3x, so it just goes up like gangbusters like that. Slope 3, right? All right, so this is an interesting example, I suppose. So, can you guys tell me what's the domain? So there's y equals f of x, we've graphed it. The domain of f of x is, like you said, minus infinity to infinity. Cool. What's the range?
Also negative infinity? And not even, does that matter?
Well, we can definitely go minus infinity all the way up to 4. Include that guy, right? But notice the thing. If I get out my hideous Carolina blue, oh, here it is. Foul color, but it's different. See, if I look at y, which is between 4 and 5, my bad. Oh man, wait a minute, 15. I'll get it eventually. That's up at 15, right? So between 4 and 15, if you draw any like horizontal line, you never hit the graph, right? You see that? Never slices through. In other words, the y values are not hit from like here all the way to here on the y-axis, right? From 4 up to 15, these values right in here, these are missing. I never attain those values. They're not in the range. So the range is just minus infinity to 4, because we go all the way down here, right? We keep going down, down, down there. But here, we have union with 15 to infinity, and that would be the range for this one. Because the domain is defined for every value of x. So every x value, there's something happening. I have a recipe for every x, there's an output. Again, in this example, for every x, there's something happening with the domain. Here, let me show you one where that's not the case. We could have something like f of x equal to, I don't know. 3 minus x and x squared plus 3. This would be, say, if minus 4 is less than x is less than 0, and if 0 is less than or equal to x is less than or equal to, let's say, 2. This one will have a domain which is not all real numbers. Like this one, if you just, I don't even need to graph it or anything, I can just look at these and tell you that the domain for my function would just be, I go from minus 4 to 0, pick it up again here, go all the way to 2. So like the domain would be minus 4 not included to 2 included. If my cases didn't glue together, I could be missing something too. I could have like a union. I could have made the first formula go from like minus 1 to, from like minus 4 to minus 1, and then I could have made the other formula go from like 3 to 7. And then the domain would just be a union of like minus 4 to minus 1 and 3 to 7. You can do whatever you can imagine you can do for domain here. Now this one, anyway, any questions about this before I go on here? So this one here, I'm just going to graph. because we know the graphs of these functions, right? That's 3 minus x. That's a line, right? Y equals 3 minus x is a line with slope -1 and a y-intercept of 3. So that would look like this. Now it goes to -4. It should go where? 3 minus a -4 would be 7, right? So it goes up to about here-ish. It doesn't get there, right? But it would, in principle, go to -4 minus a minus 3 minus a -4 would be 7. So this point is where it doesn't quite get there. But if we were to put equality, if we were to put equality on that case, it would actually get there to that point, right? And then what happens? Well, you've got y equals x squared plus 3. Well, what's that? That's a parabola, right? That's a parabola. It's not the whole thing though, because it's just 0 to 2. So it starts at 3, right? So I fill in this dot right here, basically. And if I go and plug in 2, what do I get? F of 2 is, well, 2 squared plus 3. Oh, that's funny. It's 7. Oh, that's cool. I wasn't planning for that, but there it is. So just like that, right? Now, the first two examples that I gave you guys were examples of functions which were not continuous, right? Now this one, in contrast, is what's called continuous. Why is that? F of x. They go off each. What'd you say? The lines are connected. That's good. Yeah. So here's what people usually say: a graph is continuous, or a function is continuous on a domain, if you can draw the graph without lifting your pen. See that? In contrast, if I try to draw the graph in these previous ones, I cannot help but do what? I have to lift the pen to get to the next one, right? But anyway, this is continuous. What's the domain? Well, I already said the domain up here. What's the range? I guess I should probably label this gluing point is what? It's 0, 3, right? Yeah. So I heard a 3 included, right? 3 to 7. Is the 7 excluded or included? It's included because this point over here puts it in there, right? Because you got this 2, 7 point over here which includes it. Those are the y values which we get to. Does this make sense? We can talk about some other language. For example, where is this function decreasing? The red part of the graph, the function's decreasing. So it's decreasing on -4 to 0. This function is increasing on 0 to 2. And it's continuous on its domain. Now, if we go back to example 2, we can also talk about where that one's increasing or decreasing. And you can also talk about it being continuous. This is a little bit more. Like, it is true if you restrict your attention, right? If we just focus on the purple part, it's continuous. See that? Continuous here. It's just not continuous if I also have to extend the story past the purple part, right? So if we just restrict our attention to, say, minus infinity to -5, it's continuous there. If I just restrict my attention from -4 to 5, it's continuous there. If I just restrict my attention from 5 to infinity, it's continuous there, all right? And likewise, it's increasing on the purple part. It's decreasing on the red part. And again, it's increasing on the green part. So there's some questions in the homework, the recommended homework at least, about increase and decrease and continuity, and I just wanted to mention these ideas to you. We good? All right, so I hope that helps you on the case-wise defined functions. I'm going to go on now and talk to you guys about the standard examples and transformations of graphs. So let's get into it. hopefully without coughing too much. Oh. Man, that marker really does not want to come off. So in terms of how we graph things, there are a few different ways to do it, right? Like one way, how do you graph a function? Well, one way you could just pick like 10 values, plug the numbers in, find out what they output to, then that gives you 10 points. You graph those carefully, kind of connect the dots, and that will give you some kind of picture of your graph, right? That's one way you can graph functions, just by making a table of values, by generating a bunch of data to plot. This is very, very slow as a method of graphing because it takes time to plug numbers into formulas. It's very, very slow. So we really want a better method for graphing. And so these are our standard examples. And what we're going to talk about is that we can take these standard examples and we can transform them to make lots of new examples. All right, so if we learn about just seven basic examples, then we can do quite a bit with it. So let me do here. 1, 2, 3, 4, 5, 6, and finally 7. And I need a little axis for each. I'll draw the graph in a different color. And you need to memorize these, basically. Now, I say that, but of course, truth be told, I do let you bring a formula sheet, right? So I guess I should really just tell you, make sure these are on your formula sheet and you know what they mean, right? So start out with this guy. Then I'll talk about this guy. Then I'll talk about this character here. Then I'll talk about this character here. Then I'll talk to you guys about this one like so. Then like this one, like this. And finally, last but not least, the weirdo like that. These are my 7 standard examples. We can make pretty good use of just these. Now each one of these, I want to write for you the equation. All right? So the equation for this one is, you guys tell me, y equals what? X squared. This is the square function. This one, y equals what? Square root of x. This is the square root function. This is the square root. What's this one? I heard an x cubed. That would be correct. And we call this one the cubic. And down here, you've got y equals the cube root of x. This is the cube root function. Cube root function. You notice the similarity in the shape? So like you take the square function, you turn it on its side. This is half of a parabola. That's what the square root is graphically. It's like half of the parabola. Okay? The cube root function, we just kind of like flip it on its side too. It's exactly this here. Right? How about the next one? I talked about this a little bit in the video. This is y equals, I think is it the video or last one? I can't remember when I did this. It's either Friday or Wednesday. It all runs together for me. But that's the y equals 1 over x graph, which when I came to it in the example in class before, we came to it from the perspective of xy equals to 1. Same animal. This is, I would call this the reciprocal graph. Now geometrically, what is this? What shape is this in terms? Looks like a triangle. A kite. You're not wrong. But if I did it better, it would look like a hyperbola that's been just turned. So remember hyperbolas? So if you have a hyperbola, these are the asymptotes. The hyperbola might look like this. So if you just kind of turn that, you get this. It's actually a hyperbola rotated 45 degrees, truth be told. Now, anyway, that's a graph. This one is y equals 1 over x squared. This is, well, I mean, I don't know its official name, but I always call it the volcano because, you know, come on. And then last but not least, we have y equals, exactly, y equals absolute value of x. There we go. Cool. So these are our standard examples. We can use these to make tons and tons of new graphs. So let's see how that goes. So there's a theorem that we need to learn. Here's the theorem. Given well, let's say there's the graph of y equals to f of x plus c is obtained by shifting y equals f of x up c units. Next, the graph y equals to f of x minus a is obtained by shifting y equals f of x right a units. So both of these here, I'm assuming that a and c are both positive for the sake of discussion. So this is the graph transformation theorem. All right. And if c was negative, then instead of going up, it would go down, right? And if a was negative, instead of going right, it would go left. Okay? Let me just illustrate with the examples rather than even writing it in the theorem, if that's okay with you guys. So let's start out real easy. Example, what am I on? 4. Example 4. How about I have y equals to 3 plus the square root of x. So how should I do this? What I do is I start by just reminding myself what the standard example that's related to my example is, which is square root of x. That's like this down here. Okay, there's y equals square root of x, something like that. Then, what am I trying to do? I add 3 to it, right? So what's that do? Very simple, just moves it up 3. So I just shift the graph up 3 units, and same pattern, but like this. There you go, graphed. The key feature here is that a starting point is 0, 3, right? Whereas the starting point of the standard one is 0, 0. So to be sure you're graphing correctly, you might track like where that characteristic starting point is. That might help you. Let's do another one. Example 5. What if we were looking at y is equal to the square root of x minus 4? So here's my standard square root, like that. These are all sketches, right? If you wanted to be more exact, you get graph paper or do stuff. But I will ask you maybe just to sketch a graph if I forget how horrible it is to grade them in my foolishness right before writing the test. But I have at times asked students to actually make graphs. So stupid, so stupid. Anyway, it's much more fun to ask you to decide which graph is which. You know, I learned just about as much from that. So I'm supposed to take this graph and do what? Shift it 4 units to the where? Right or left? You would say left, but it is right, yes. So for like over here.
Why is it to the right?
Well, let's think about that. This point right here, in the regular one, in the standard example 0, 0, right here, I'm claiming that that point should be 4, 0. Does that make sense? When you plug 0 into, excuse me, when you plug 4 into this, do you get 0? Well, I get 4 minus 4, square root of 0, 0, so it checks. Now, while we're talking about it, let's make a hideous graph to the left 4 units, like this. That would be y is equal to the square root of x plus 4. Now, the starting point there, minus 4, 0, right? So what happens when you plug minus 4 into that formula? You get square root of minus 4 plus 4, which is 0. So it checks, right? I mean, I understand, like you're tempted to think because there's a minus, it must be going left. Because a plus is supposed to be going right, but it's just not how it works. And the reason that there's this distinction is, on the one hand, we're adding to the output, but on the other hand, we're shifting the input. There's an asymmetry in the roles here. X and Y are different with respect to y equals f of x. Yeah?
It looks like a road.
Looks like a road? Yeah, it should really look more like a road if I was better at my... This one should be more curvy, you know? But anyway, I'll stop. Thank you. Very helpful. Example 6. I guess I'll do it on the third board. So, example 6, suppose we're up against y is equal to, let's say 2 plus 1 over x minus 3 squared. So how would we deal with something like this? Well, what's that? Up to? Okay, so how about this? We start with y equals 1 over x squared. That's kind of our basic function here. And then if I go to y is equal to 1 over x minus 3 squared, that's one step I can make, right? And then I can do another step, which is y is equal to 2 plus 1 over x minus 3 squared. And then I would get to where I'm trying to get to, right? So this is a two-step thing. Step 1, we go right 3, right? And then we do what? We go up 2. Right 3, up 2. So if I graph the volcano, right, it looks like this, right? But the other thing to be more careful with the volcano is to understand it's got a horizontal asymptote and a vertical asymptote, which we need to track. So the square root's got this point, right? The vertex on the parabola it's half of. We can kind of track that to understand the graph of the square root function. But this one, we really want to track this guy and this guy, right? Because what are those? Those are the asymptotes. In particular, we have y equals to 0 is a horizontal asymptote, and x equals to 0 is a vertical asymptote for this graph, which I abbreviate as HA and VA because writing out asymptote does not give me joy. So if you shift the graph, a simple way to think about how to do it is just to shift the asymptote. So I just need to make the asymptotes go right 3 units and up 2. And that will show me where the graph needs to be. So my new asymptotes for the final product here are at 3 and 2. And my volcano looks something kind of sort of like this. It should be like symmetric and stuff with respect to the asymptote. But roughly speaking, there you go. That's what y equals this. Looks like that. And now you guys could tell me stuff like, what's the domain, what's the range of this function, right? That would be easy. The domain would be everything except for, what? Except for minus 3? Excuse me, 3, thank you. Everything except for 3. What's the range? Yeah, if I call this thing f of x, so I said the domain of f was minus infinity to 3 unioned with 3 to infinity. What was the range? 2 to infinity. 2 included or excluded? Excluded, right? All right, so this is the start of the transformation by graphs problem, but there's certainly more more to talk about. Like, we still need to talk about, you know, reflections and like stretching vertically or stretching horizontally, those things, yeah. And I haven't, you guys got to stop me. I got to turn the attendance sheet out here. So if you were here last time but you left because you thought I wasn't coming, I mean, true, but you can check here. Check like yesterday and today if you don't mind. Can you add a 10-2 on the top there? Well, that's filtering around. Let's look at a couple problems on the projector in the minute or two that remains here. So these are really, like some of the recommended homework problems, they're very, very simple, but they're worth discussing just for a minute, just for the sake of making sure we're all on the same page here. So, oh, I guess you guys want me to top hat too, right? Come on, you. Well, it's about time. Give it a talking to. 22:34 apparently. All right, we got that. Okay, so, oh, good grief. So you guys tell me, now that you know about transformation by graphs, can you tell me what's going on here? Which one's which? I mean, well, you're like, well, these are parabolas, so we already knew how to do this anyway, right? But you ought to be able to make really quick work of this now as you think about the transformations of graph idea, right? Like, for example, let's look at this one. X plus 2 squared plus 1. That is shifting left 2 units and up 1. That one. Right? How about this one? I shift right 2 units and up 1. So that's got to be this one, right? This one is just x squared minus 2. That's the standard parabola shifted down 2. That's this one, right? Second, let me go back to the previous page here. We talked about those already. How about this? Can you tell me these functions here, which ones are continuous everywhere? Well, I can draw this one, and I can draw that one, and I can draw this one, and I can draw this one without lifting my laser. So this, and that, they're everywhere continuous that they're defined. On the other hand, this one is continuous from minus infinity to 3, but then I have to turn my laser off, whoop, turn it back on over here to keep going. So this is not continuous everywhere. Any open interval that contains 3, it's not going to be continuous on that because there's a hole in the graph. So if there's a hole in the graph, it's not continuous there. So we either have to go from the left or from the right to approach such a silly feature. Right? Likewise here, there's a hole in the graph. So it'd be like continuous minus infinity to 1, and then again from 1 to infinity, but not on any open interval which surrounds 1. So once the attendance sheet makes it to the last student, class is over. So almost there. How about this one? Which one of these is not continuous? That's continuous, 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 that's continuous. This one is very much not continuous. It's like like there's infinitely many discontinuities, one at every integer. Hop, 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 right? This is like rounding down or something. Or no, this is the always round down function. You know, like give me 0.5, what's it spit out? 0. 0.7, 0. If you give it 1.7, what's it give you? 1. See, like it always rounds down. It's the rounding down function. Okay, anyway, that's what the graph of rounding looks like. Exciting, right? That's not entirely true. Of course, the real rounding based on some kind of complicated rule with half integers, blah, 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 blah. But hey, that's it for today. Thanks, guys.